I'm Emma Reed,
And I'm Lucine Gamigian.
and this is Deep Reinforcement Learning Applied to Pac-Man. And this is just a quick outline of everything we're going to be talking about in today's presentation. For reinforcement learning, we have an agent acting on its environment. So here our agent is Pac-Man, the environment is the maze itself. Its actions are it running around doing up, down, left, and right, picking up the goals as it goes through. We reward it positively for picking up goals, negatively for running into the ghosts or walls or just moving around randomly. So Q-learning is a classical way to do reinforcement learning. So you basically construct a table of states and actions where the entry is the corresponding Q value if you were to make that action from that state. And the Q values are updated using the Bellman equation below.
We'll use a deep Q-learning. Deep Q-learning combines the classical, the Q-learning algorithm with neural networks. Deep Q-learning neural network takes in the state as an input and outputs the Q values corresponding to all the possible actions. Deep Q-learning incorporates the following methods to make the learning better. Epsilon grid exploration, which helps to explore the environment at the beginning and to stick to good policy at the end. With probability epsilon, the agent is making random actions, and with probability 1 minus epsilon, the agent is making actions that will maximize the Q value. In our case, for example, we start with epsilon is equal to 1, and as time passes by, the agent becomes more and more greedy, and we decrease the epsilon gradually to 0.02. This allows the agent to discover states that will give it higher rewards than if it just followed the greedy policy. And then we have replay buffer, which stores the previous experiences in a large buffer, and then we sample a certain amount of those and then feed that into the neural network to train our neural network. The experience size of the experience buffer should be some large number. In our case, we take 10,000, and then we just collect the experiences. So the experience buffer helps the agent not to forget the previous experiences, but also using the experience buffer, the data is not correlated, is not too close to each other. And we also have a target network. We keep a copy of the network, and you see from the training network. And this helps with the oscillations and makes the convergence better. In our case, we copy the training network to the target network once in every 100 steps. The following is the deep Q-learning algorithm. So we initialize the experience replay, we initialize the training neural network and target neural network, and then we initialize the state, and then with epsilon greedy policy, we take the action and move the agent, and then store that transition, which is the state, the action, the reward the agent gets, and the next action, next state. And then we sample a random mini batch of the transitions to feed into the neural network. The step 11 is the formula that updates the target Q value. Here, the maximum is taken over actions that maximize the target Q value. And then we calculate the loss, which is just the MSE loss, and then we update the training Q values using the stochastic gradient descent. In our case, we just used Atom because it was faster. And then every 6 steps, like I said in the previous slide, every 100 steps, we copy the weights of the training network into the target network.
Here we have an example of what we'll be passing into our neural network. On the left is Pac-Man with the Tkinter setup. On the right is a NumPy array equivalent of it. So what we can see now on the left is that you'll be able to see a video of what it looks like as Pac-Man is moving around.
We have used 3 different deep Q-learning algorithms. Deep reinforcement learning algorithms, deep Q-learning, double deep Q-learning, and dual link deep Q-learning. So deep QN and double deep QN, they have the same architecture. We have 3 convolutional layers and a fully connected layer. The only difference between the two is the formula in which way we update the target Q value. Here, Y and Q of S of T and A of T are the same thing. And then in case of DQN, we are taking the maximum over the actions that maximize the targeted Q value. And in case of the double DQN, we first take the action that is maximizing the training Q value, and then we take the target Q value of the state if we were to make that action that maximizes the training Q value. And then dual link DQN consists of 3 convolutional layers, and then the difference is that after that we have 2 fully connected layers. One of the fully connected layers, the one on the right side, it gives us the state of the value of the state, and then the left side, it just outputs the advantage, and then which is if we make an action, how much better it is if we were to make another action, and then we put them together, and after that we output the Q value.
What we noticed basically immediately when we were training was that the model takes a long time to train and learn even. A lot of the papers that we were reading would say that it takes upwards of 250,000 to 1,000,000 iterations depending on how complex the task is.
Here are some of the results that we have. We applied the DQN to a 4x4 grid with 3 ghosts, 1 ghost, and 2 obstacles. So like Emma said, it takes a very, very long time to train. So here we run it for about 2,500 episodes. This is the loss function, and we can kind of see like it is going down, it is getting smaller. And then after 2,500 runs, when the game, when the episodes, we run out of the episodes, we loaded the saved weights after 2,500 runs, and then we run it again for another 1,500, and then again we can see that the loss is very gradually decreasing. These are the rewards, and so since the agent doesn't really have time to learn, the rewards are mostly negative. Once in a while we would get positive rewards, but again it needs a lot of time for it to learn the game and then actually constantly get positive rewards and maximize them. And here is just the win number as time goes on. It is winning more, and it's like the win rate was in this case was about 40%. We also applied double DQN and the dual link double DQN to the same environment, and we kind of were expecting that the results will be better, but we can see that the loss is not that good and in both cases. But we are expecting, if we were to run it much longer time, double DQN and dual link double DQN would be much better than just the regular DQN.
We believe why our agent didn't learn was mainly because it needs to be run for a much longer time. Additionally, while the experience replay is valuable, it would be better if it was only looking at the positive experiences, so showing it how to win and get positive rewards. And additionally, another thought that we had was decreasing the epsilon only when we win, and decreasing it slowly enough so the agents still have time to learn and explore. As we've said before, DQN takes a very long time to train for Pac-Man, even with a minimal number of goals and ghosts. You also need a lot of data for it, and especially the right data, so specifically scenarios where Pac-Man wins. And DQN seemed to be better from the initial runs. However, we do expect that the double and dueling DQN would become better as we run longer. So in the future, if we were to expand on this assignment, we would try prioritized experience replay. We would train with more goals and more ghosts. We would train the ghosts to move randomly rather than the current situation where the ghost is just in one spot. Then we would try to have the ghost catch Pac-Man, and then we would have the same neural network or different neural networks controlling the agent and the ghosts.
Thank you.